So far, we've learned to build circuits that can calculate. But there was a problem. A logic gate only responds while the signal is present. When the signal is gone, the result is gone too. How can you continue a calculation if the machine forgets what it just did? A gate can respond, but it can't remember. Every signal fades away, nothing stays behind. I needed a way for a value to stay, waiting for the moment to be used again. The solution came with an elegant idea. What if the output of a circuit were fed back to its own input? This principle is called feedback. Instead of disappearing, the circuit can now keep its state. In 1918, William Eccles and Frank Jordan described this principle. First vacuum tubes, then transistors, then silicon. But the idea stayed the same. Every limit we encountered, someone found another way. Every unanswered question brought a brand new way. The history of learning is the story of never stopping. Two gates together, keeping each in place. They help each other keep their state. No magic, no secret, no hidden hand behind. Just a clever circuit, keeping one bit safe. This circuit has an important name, flip-flop. It can hold just a single bit, 0 or 1, on or off. But that's enough to store information. And when several flip-flops work side by side, a register is born. One alone holds little, just one single bit. Many working together, holding numbers still. 8, 16, 32, each one in its place. Side by side together, form a single register. Think of the register as a small workbench while the machine calculates. Values wait right there. It's not the main memory, it's temporary storage. Fast, ready for the next step. Without registers, every calculation would have to start over. Now the machine can hold before moving on. Every step of the journey won't be lost or gone. But holding is not enough, we still need control. Who decides each step? Who gives every command? Every limit we encountered, someone found another way. Every unanswered question brought a brand new way. The history of learning is the story of never stopping. Now we know how to calculate. Now we know how to store. But who decides when to calculate, when to store? Who controls the whole sequence? That answer comes in the next part. In the last part, we met the control unit. It coordinates the whole machine. It fetches the instruction. It decodes it. It executes it. But to coordinate is not to calculate. When the order comes, add these two numbers. Someone has to do the math. That component exists. Its name is arithmetic logic unit, or simply ALU. We have gates for logic, registers to hold. We have a control unit, but who will do what it's told? When an instruction comes in, someone has to do the math. Take two values, do the work, send the answer back. The ALU does not make decisions. It does not choose what to do. The one who sends the order is the control unit. The ALU just executes. It adds, subtracts, compares values, performs logical operations, and sends the result back to the registers. Every limit we encountered, someone found another way. Every unanswered question sparked a brand new idea. The history of learning is the story of never stopping. Two inputs arrive, two values to combine. It does just what it's told, no need to improvise. It doesn't choose, doesn't invent, doesn't need to understand. Its job is to execute exactly what was planned. But how can a machine actually add? It all starts with just one bit. 0 plus 0.
0 plus 1.
1 plus 0.
1 plus 1.
Just 4 possibilities. In one of them we get a carry. This circuit is called a half adder. When you add the carry from the previous position, you get a full adder. Connect several together and you can add numbers with as many bits as you need. And or not working, each gate in its place. There is no other secret, just knowing how to arrange from the parts we already know. A new circuit comes alive. No magic was born here, just a circuit that can add. This might be the most important secret. The ALU did not come from a different technology. It uses exactly the same logic gates we've seen from the start, just arranged in a different way. In 1945, John von Neumann described it as the central arithmetic part. The name ALU would come a few years later, but the core idea was already there. Registers hold it all, the control unit directs, but who does all the math? That's the ALU's job. Now the machine is growing, each part has found its place. Still we need to understand how numbers take their form. Every limit we encountered, someone found another way. Every unanswered question sparked a brand new idea. The history of learning is the story of never stopping. Now we know how to store. Now we know how to control. Now we know how to calculate. But there's a question, still waiting for an answer. How does a circuit made of only zeros and ones represent the number 5 and 100 and a negative number? That is the next step in our story. Yeah. Now the machine can calculate, it can store results. But there's still a problem. Who decides when to calculate, when to store? Which register should get the value? No logic gate knows that. No register knows that. There had to be a component to coordinate it all. Each part knows its job. Each part knows how to respond. But alone it can't tell when its turn will come. Store today, calculate tomorrow. Everything needs a sequence to make the parts as one. This component is called the control unit. It does not calculate. It does not store information. It coordinates. It fetches the next instruction. It decodes what it means and sends signals to the right components. Every limit we encounter, someone found another way. Every unanswered question sparked a brand new idea. The It keeps every step in time, never needs to improvise. Everything follows the same rhythm, together as one. Each part waits for its moment to begin its work again, and the whole machine learns how to work as one. For many years, changing a computer meant changing its wiring. In 1945, John von Neumann described a different idea. Instructions could be stored in the same memory that holds the data. Just change the program. The machine could perform a different task without rewiring its circuits. First fetch the instruction, then decode what it says. When it knows what it means, it tells each part what to do. Fetch, decode, execute, and repeat. This rhythm drives every computer's beat. To know which instruction comes next, there is the program counter. The instruction being executed stays in the instruction register. Meanwhile, the control unit coordinates every step. Fetch, decode, execute, and start again. Registers hold it all. The ALU does the math. Control brings every part together at last. But one mystery remains, waiting to be solved. How do numbers become zeros and ones to count? Every limit we encounter, someone found another way. Every unanswered question sparked a brand new idea. The history of learning is the story of never stopping. We know how to build circuits that calculate. We know how to store values. We know how to coordinate all these operations. But we still need to understand one of the most important ideas in computing: how to represent numbers using only zeros and ones. That is the next step in our story. We built a remarkable machine. We store information in registers. We coordinate operations with the control unit. We calculate with the ALU. But one mystery still remains. When the ALU adds two numbers, what is it actually adding? When a register stores information, how is that information represented? Inside a circuit made of flip-flops. How does the computer, which only knows two states, manage to represent any number? A transistor has only two states: on or off, current or no current. But that's exactly what makes it all possible. Two pure states, and the world is explained. Think about the decimal system. You know it has 10 symbols, 0 through 9. When it reaches 9 and wants to go beyond, it doesn't create a new symbol. It uses position. The number 10 is a 1 in the tens place, plus a 0 in the ones place. Each position is worth 10 times the previous one. The computer does exactly the same thing. The difference: it has only two symbols, and each position is worth twice the previous one. Decimal is 10, binary is 2. Same logic, same form, only the base changes. 1, 2, 4, 8, 16. Powers of 2 in a line. Each place you climb doubles what was behind. 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0. The counting never stops, and every number can be built. The number 5 becomes a pattern of bits. A pattern: 1, 0, 1. 4 plus 1, 5 again. Let's count in binary. 0 is 0, 1 is 1.
1, 0 in binary is
2 in decimal.
1, 1 in binary is
3 in decimal.
1, 0, 0
In binary is 4 in decimal.
1, 1, 0, 1 in binary is
5 in decimal.
1, 1, 0 1.000 in binary is
8 in decimal. It's the same logic we use to break down 257 into 257. Now in powers of 2, not powers of 10. A register holds 8 flip-flops side by side, 8 bits in a row, holding information with 8 positions, 256 different combinations from 0 to 255. Each flip-flop holds 1 bit. An 8-position register holds 8 bits. How many different values can it represent? Each bit can be 0 or 1, with 8 independent bits. The total number of combinations is 2 times 2 times 2 times 2 times 2 times 2 times 2. 256 values from 0 to 255. Adding in binary is just like normal addition, place by place, and the carry moves along. 1 plus 1 is 1 0. In this writing of 2, leave 0, carry 1, just like we always do. Remember the half adder in the ALU? It adds 2 bits and produces a result and a carry. That carry is exactly what happens in the second place. When we add 1 plus 1 in binary, the result is 0 in the current place, and a 1 carried to the next. The ALU does no magic. It adds binary numbers place by place, just like we add decimal numbers, only with 2 symbols instead of 10. Why does the computer choose this way? 2 states in a circuit, on or off. No need for 10 different voltage levels. No confusion, everything clear and safe. The choice is practical. Electronic circuits have 2 natural states, on or off. Current flowing or no current. Transistor open or closed. Trying to represent 10 different symbols would be much harder. It would need to recognize 10 different voltage levels precisely. Any variation, any noise would cause an error with 2 states. The distinction is simple and robust. A high state represents 1. A low state represents 0. That simplicity is what makes the computer possible. Leibniz saw this idea 300 years ago. Said that zeros and ones could build any number. Boole created Boolean logic. Shannon linked logic to circuits. Von Neumann joined the parts, and binary found its place. The binary system was not invented for computers. Gottfried Wilhelm Leibniz, in 1703, published a paper, Explanation of Binary Arithmetic. He showed how all numbers could be represented using only 0 and 1. Leibniz was fascinated by the philosophical simplicity, creating infinite complexity from just 2 symbols. But it was pure mathematics. There was no technology to make it practical. 150 years later, George Boole formalized an algebra based on 2 states, true and false, 1 and 0. And in 1937, Claude Shannon showed that this algebra could be implemented directly in electrical circuits. 3 thinkers apart, each one in his time, Leibniz, Boole, and Shannon, building the same road. The ideal Leibniz dream became a machine in our hands because von Neumann understood how it all fit together. Now it all makes sense. The register that holds the ALU, that calculates the control, that coordinates all work with these bits. Flip-flops hold bits, registers hold bits. The ALU computes in binary, control coordinates in binary. They all speak the same language. Finally, we understand the 4 pillars of any computer. It can store, because registers hold bits. It can calculate, because the ALU turns bit patterns into new patterns. It can coordinate because the control unit sends bit patterns as instructions. And it can represent because each bit pattern gains meaning in the binary system. Now we know how the computer stores, how it calculates, how it coordinates, and what is the language that ties all these parts together. The computer speaks binary, and now we understand too. But one bit alone is almost never enough. Computers work with groups of bits. How do these groups form the units we use every day? That is the story of our next song, The Byte. The Byte. In Part 5, we learned that a bit is 0 or 1. We learned that any number fits in this language. But here's the problem. One bit alone is almost never enough. How do you store a letter? How do you store a keyboard character? One bit can't do it. You need a group of bits working together. One bit is small, 0 or 1, nothing more. But when you join many together, something bigger is born. Groups of bits side by side form a single whole, a unit of information one bit alone could never hold. But there was a serious problem. Each computer organized its bits differently. One maker used 6 bits, another used 7 bits, another used 9 bits. There was no standard. A standard was needed. How could these groups of bits be organized? So every computer understood the same thing. Every machine was different, 6 bits, 7, 9 as well. Each machine stored data in its own different way. There was no understanding. There was no agreement. It needed a standard across the industry. Every limit we encountered, someone found another way. Every unanswered question sparked a brand new idea. The history of learning is the story of never stopping. In 1956, Werner Buchholz was facing this problem. He needed a name for this group of bits. He needed a clear definition. The term byte was born, a name for a group of bits, but its size still varied. The answer would come later. Werner Buchholz was looking for a name for the unit. He called it a byte. The standard would come later, a name for the groups that each machine created. But what would be its size? No one knew the size yet. But the story did not end in 1956. The byte was a good idea, but the industry was not yet convinced. There were still computers using groups of bits of different sizes. There was still conflict. There was still no standard. Then, in 1964, came the IBM System 360. It was a revolutionary machine, and it defined the byte as 8 bits. The industry converged. The standard was set. 8 bits became standard. With the System 360, the industry converged to a single standard. Now all understand when they talk about a byte, 8 bits is 1 byte. In the same standard. See how this matters. Before, there was chaos. After, there was a standard. A byte came to mean the same thing across most of the industry. 8 bits, it's the standard. Now all the components of this series make sense. Registers hold bytes. The ALU calculates bytes. The control unit coordinates bytes. All use the same language. Bits are the seed. Bytes are the tree. But how does the machine store these bytes? Where are they kept? How do you access them when needed? That is the story of our next song, Memory. So far we have learned how to store in registers, how to calculate in the ALU, how the control unit coordinates everything, how bits form bytes. But a question remained unanswered. An entire program has thousands of instructions. A dataset can hold an immense amount of values. No register can hold all of that. Where does all this information go? There has to be a bigger place, a place that holds large volumes of information, a place where the computer can find any value when it needs it. That place is memory. Registers are small, they hold values in action, but a whole program needs a much bigger place. Memory is the answer, a vast space where everything the computer needs is kept safe and secure. In memory, each location has a number, a unique address. When the computer needs a value, it says, fetch the value at address 1000. When it wants to store a result, it says, put this value at address 2500. It's like a system of numbered boxes. You store something in any box and retrieve it later, as long as you know the box number. Each address is a specific place. Each address holds a unit of information, or several, depending on the architecture. Each address is a number. Each number marks a place where information is kept, waiting to be found. 1,000 addresses, millions each, with its own space, all organized for the computer to fetch. But at first, this was a challenge: how to store information safely and quickly. The first computers used different technologies. Each had its own solution. There was so much to invent. Each machine looked for its own way. The Williams tube stored electric charge on its screen. The mercury delay line made pulses circle around. No hurry, no rush, just waiting for its turn. Every limit we encountered, someone found another way. Every unanswered question sparked a brand new idea. The history of learning is the story of never stopping. In 1946, Freddie Williams began developing a way to store information using a cathode ray tube, the same component used in televisions. Tom Kilburn worked with him. Jeff Tootle helped build it. On the 21st of June, 1948, the Manchester Baby, the first stored program computer, used this Williams tube to hold its instructions and data. It was random access, fast but unstable. The charges faded. They had to be constantly rewritten. Other machines used the mercury delay line, sound pulses traveling through tubes of mercury. When they reached the end, they went back to the start, circling continuously. It was more stable, but slow, sequential. You had to wait for the data to circle back. The Williams tube was fast, but far too fragile. The delay line was slow, and access was sequential. Something was missing that joined both speed and trust. A technology that could store and let us reach it directly. The answer came in 1953. J. Forrester perfected a technology that had been discovered by several researchers: magnetic core memory. Tiny rings of magnetic material, smaller than a pinhead, threaded with wires forming a grid. Each ring held one bit. Magnetized one way meant 1, the other way meant 0. The wires passing through each ring could sense and change the magnetization. Rings of magnetic material, smaller than a pinhead, each one holding a bit in its magnetic direction. Wires passing through, reading and writing, forming a network that held information. And there was a crucial advantage. Magnetic cores held data. Even when the computer was turned off, they were non-volatile. Unlike the Williams tube, which lost data in fractions of a second. The magnetic core held information even when power was removed. There was a technical quirk. Reading a core erased the data in it. It had to be rewritten immediately after each read. And Wang was one of those who solved this problem with the write after read cycle. It remained non-volatile from the user's point of view. The cost was high at first, almost $1 per bit. But women with steady hands, with microscopes and precision, threaded thread the tiny rings onto wires at industrial scale. Work of precision done in factories. Magnetic core memory spread faster, more reliable, non-volatile. Advantages the earlier technologies did not offer. IBM bought Wang's patent for $500,000 in 1956. With the money, Wang founded Wang Laboratories. Later, IBM would pay mighty $13 million for Forrester's rights, the largest patent deal up to that time. Core memory came to dominate computing. It was in IBM computers. It was in the guidance computer of the Apollo program. It was in countless other machines of the 50s, 60s, and early 70s. Magnetic core memory that truly held on fast, safe, reliable. The technology that dominated computing, woven with precision by working women, building the future with dedicated hands. Now everything fits together. We learn to make circuits that calculate. We learn to make circuits that hold momentarily. We learned how information is represented. We learned where information is stored in large volume. We now have all the fundamental building blocks of a computer. Bits are the seed, bytes are the tree, memory is the forest. But there is something we haven't looked at closely yet. How do these blocks work together? Instruction by instruction. How does the computer go from the first instruction to the last? How does it know what to do next? That is the story of the next volume. The processor cycle.